In this section, we will introduce the idea of a relation, and more specifically, we'll look at which relations satisfy the conditions to be named functions. We'll look at domain and range of functions, the vertical line test, and we'll also look at some of the basic types of functions. Let's start by talking about what a relation is. A relation is a correspondence between two sets, A and B, such that each element of set A corresponds to one or more elements in set B. If we can say this a little bit more simply, a relation is simply a set of ordered pairs. So let's write that as an equivalent definition. Set A is called the domain of the relation, and set B is called the range of the relation. Again, put more simply, the domain is the set of all x values, and the range will be the set of all the y values. A function is a relation, but it has a condition that must be met. A function is a relation such that for each element in the domain, in other words, for each value of x, there is exactly one corresponding element in the range, meaning there is only one corresponding y value. Another way of saying this is that there cannot be two ordered pairs that have the same x coordinate and yet have different y coordinates. So we can say that in a function, no two distinct ordered pairs can have the same x coordinate. Or in other words, no two ordered pairs can have the same x. So no repeated x values. Notice that this doesn't say anything about the y values. Those can be repeated. Let's look at the following example. This is called a map. And let's assume that in the first figure we have x values, and in the second we have y values. This mapping represents three ordered pairs. The ordered pair Phoebe, comma, 5 foot 5 inches. That's one ordered pair. The next is Amy, comma, also 5 feet 5 inches. And lastly, Katie, with a corresponding y value of 3 feet 1 inch. So notice that both Phoebe and Amy could have the same height of 5 feet 5 inches. The y value can be repeated for two different x's. But no one x value has more than one coordinating y value. So for example, Phoebe couldn't be paired with 5 foot 5 inches and also have Phoebe be paired with, say, 3 feet 1 inch. That means that in example A, we do have a function. There are no repeated x values for different ordered pairs. In example B, we have a set of ordered pairs, so we have a relation. In this case, we have 5 ordered pairs in the relation, and we're trying to determine if this is a function or not. Well, let's see. We have an x value of 1 in the first ordered pair, an x value of 7 in the second, an x value of 8 in the third, an x value of 7 again in the fourth ordered pair. So that looks like a potential problem. The x coordinate is repeated, and yet it is being paired with different y values. So this would not be a function. Remember, we cannot have repeated x coordinates in different ordered pairs. Now we're also asked in the instructions to designate the domain and the range for these relations. Remember, this is true for relations even if they are not functions. So in the first case for letter A, the domain would include the three names, Phoebe, Amy, and Katie. And we're going to list these in curly brackets to designate that this is a set or a collection. The range only consists of two different values, the 5 feet 5 inches and the 3 feet 1 inch. And again, we'll put those in curly brackets to designate this is a set. Notice that even though the value 5 feet 5 inches is repeated, we only have to list it once because in a set, we just have to write what's included in the set. It can be repeated without having to be listed more than once. For example B, the domain would be the set of all of those x values. So we have the value 1 and 7 and 8 and 2. Notice that we did not have to repeat the number 7. It's also good to note that when we're writing the elements of a set, they do not need to be listed in any particular order. So they don't have to go from least to greatest or alphabetical order, although that could be helpful if you have a very long list. However, in set notation, order is not important. The range for this relation would be the values 9, 7, 1, 6, and 4. And again, we'll use those curly brackets to designate that this is a set. In example C, rather than having the relation as a set of ordered pairs in list form, we have the ordered pairs in graph form. So it looks like we have 5 ordered pairs in this relation. And let's go ahead and label the coordinates for each one. Here we have the origin. Here we have the ordered pair 1, -2. Up here we have 1, +4. Over here to the left, we have -2, +2. And finally, we have -4, 5. So in terms of the domain, we have the following values, -4, -2, 0, and 1. In terms of the range, we have, 5, 2, 0, 4, and -2. And to answer the question as to whether this relation is a function, I look to see if there are any repeated x values in different ordered pairs. And I do see a problem here. I do see that this ordered pair, 1, 4, and this ordered pair, 1, -2, have the same x coordinate, and yet they have different y coordinates. So unfortunately, this is not a function. So if we have the graph of a relation, one way to tell if we have a function or not is to make sure that we don't have any points that are vertically aligned. If we have any points that are vertically stacked, then this will not be a function. We're going to see this a little later in our notes, referred to as the vertical line test. All right, let's look at the following 3 relations and determine if they represent a function. In order to show that a relation represents a function, we need to show that for each x, there is exactly one corresponding y value. So let's look at example A, for instance. X squared plus y is equal to 64. If we isolate the y variable by subtracting x squared from both sides, we get that y is equal to -x squared plus 64. Now let's think about this a moment. If I were to select a value for x, and I were to substitute that value into this equation, hopefully you agree that there is only one resulting y coordinate. So regardless of my choice for x, once I make that substitution into this equation, there will be one precise y coordinate that will correspond to it. That means that this is a function. So we'll say here, for each value of x, there is only one corresponding y. Okay, let's look at the next example. In letter B, we have x squared plus y squared is equal to 49. Let's go ahead and isolate the y variable again. So we'll start by subtracting x squared from both sides. And to isolate y, we will have to use the square root property, which states that y would equal the principal or the negative square root of 49 minus x squared. Now, I think we have an issue because I can already think of a value of x that when substituted into this equation will produce more than one corresponding y. Let's look at the number 0 for x, just as an example. If x were 0, and let me just write this down. If x is equal to 0, then we have y is equal to plus or minus the square root of 49 minus 0, which is the square root of 49. So y would equal plus or minus 7. Those are two different y values for the same x value. That means that this is not a function. In fact, if you recall from our work in Chapter 2 with circles, this equation represents a circle centered at the origin with a radius of 7. If you think of the graph of the circle, certainly you can think of points that are vertically aligned, meaning that they have the same x-coordinate and yet they have different y-coordinates. So it would fail the vertical line test. Finally, for letter C, we have 6x minus 3y is equal to 6. Let's go ahead and isolate the y variable again. We'll start by subtracting 6x from both sides and dividing both sides by negative 3. So we have y is equal to 2x minus 2. Regardless of our choice for x, once we make that substitution, we will find that there is exactly one corresponding value for y. And this is true because this is a linear equation. This equation represents a line. And other than vertical lines, lines will always pass the vertical line test. In other words, there will never be 2 points that are vertically aligned. Again, the exception being vertical lines themselves. So this is the equation of a line. It's not a vertical line, so indeed this is a function. Next, let's talk about function notation. Instead of using the variable y, we sometimes use letters such as F, G, or H, and others toward the middle of the alphabet to name functions. If we want to name a function f, then for any x value in the domain, we call the corresponding y value f of x, or f at x is sometimes how we say that. This is called function notation. Now be very careful. In mathematics, in algebra specifically, sometimes when we write two letters side by side, or we write them with parentheses side by side, that indicates multiplication. That is not the case here. The symbol F, open parenthesis, X, close parenthesis, that does not indicate multiplication. It is simply a label, so it acts as a unit. Let's look at the following function. F of x is equal to x squared minus 1. And we are asked to evaluate the function f when x is 2, then evaluate the function f when x is negative 3, and then evaluate the function when the input is x minus 2. So not a constant, but an expression. To do this, we're simply going to substitute what is inside the parentheses for x in the original function notation. So for example, f of 2 would equal, we would actually substitute 2 for where the x is. And so we would have 2 quantity squared is 4, 4 minus 1 would equal 3. That means that the ordered pair 2, 3 is part of the function. Two for x, 3 for y. All right, let's do the same thing with f evaluated at x equals negative 3. So again, we're going to substitute negative 3 for x in the original equation. And in this case, we have negative 3 when squared is 9. 9 minus 1 would be 8. That means that the ordered pair negative 3, 8 belongs to the function as well. Remember, functions are collections of ordered pairs because that's what relations are, right? Sets of ordered pairs. Finally, let's look at f evaluated at the input x minus 2. Again, we're going to square the input and then subtract 1, right? That is the rule that we have to follow. Square the input and subtract 1. Well, the input in this case is the expression x minus 2. So when we square the binomial x minus 2, we have x squared minus 4 times x plus 4, and then we're going to subtract 1 from that. So we have x squared minus 4x and then plus 3. That means that the ordered pair x minus 2 for x and then x squared minus 4x plus 3 for y is an ordered pair of f. All right. Next, let's introduce an important concept that will be revisited for those of you who move on to additional math courses such as pre-calculus algebra or trigonometry or even calculus, and that is the difference quotient, also known as the average rate of change. The difference quotient is the difference between the value of f evaluated at some quantity x plus h minus the value of f evaluated at just x, all divided by that difference between the inputs, which is h. This is a very cumbersome task depending on the complexity of the function f. So we'll practice with a few examples. Certainly you'll practice more as you work through your homework assignments. But let's look at the following example. We have f of x is equal to 5x minus 1. F of x is equal to 5x minus 1. And we are asked to find the difference quotient. Now, for the sake of space, I'm going to write in between these two text areas so that we can still see the expression above. So in this case, wherever we see the input, we have to multiply that input by 5 and then subtract 1. So let's do that with this first expression. The input is x plus h. So we have to multiply that input by 5 and then subtract 1. Next, we're going to subtract f of x, which is the original rule. Multiply the input x by 5 and then subtract 1. And finally, we're going to divide everything by h. So just so that we can see what's happening, this expression here that I'm enclosing in these red brackets, that's the function f evaluated at the input x plus h. And then in the second set of parentheses, we have the original f of x, and we're subtracting those two, and then we're dividing by h. So let's go ahead and simplify this carefully by distributing. So we have 5 times x plus 5 times h, all minus 1, minus 5x, and then plus 1. Because again, we have to distribute that subtraction. In the denominator, we have just h. Again, let's simplify. Here we have 5x minus 5x will be 0 when we add. Then we have a negative 1 plus a positive 1. That'll give us 0 as well. So it looks like in the numerator we have just 5 times h, and in the denominator we have just h. So finally, after simplifying, we find that the difference quotient is equal to 5. Again, in this course, we only will teach mechanically how to find the difference quotient. You will explore its applications and its conceptual meaning as you move on to additional courses. If you're curious and want to know, it's all tied to the average rate of change, which is related to slope if we're talking about lines, but the average rate of change can also be talking about the slope of a line that's tangent to a graph, that touches a graph at one point. And so that's a concept that, again, you'll explore in future classes. For now, we're going to focus on the mechanics of finding the difference quotient. All right, let's look at another example for additional practice. So here we have a different function. F of x is equal to x squared plus 2x minus 3. And I'm going to write the equation of the difference quotient again because we've lost it here. It's f evaluated at x plus h minus f evaluated at x all over h. So in this case, the rule is you take your input and square it. Then you take the input, multiply it by 2, and add it to the first result. And then finally subtract 3. So let's work on f evaluated at x plus h. You're going to first square the input, then multiply the input by 2, add those together, and then subtract 3. So this is f evaluated at x plus h. Like we did before, I'm going to put this in little red brackets so that we can see that that's the first term in that numerator of the difference quotient. Next, we're going to subtract f of x. And f of x is, if you look at the original function, x squared plus 2x minus 3. And we're going to divide all of that by h. Now it's just a matter of simplifying this as much as possible. So first let's square the binomial x plus h. That gives us x squared plus 2 times x times h plus h squared. Next we're going to distribute the 2 here, so we have plus 2x plus 2h, and finally we'll have minus 3. For the second part of the numerator, we simply have to distribute that negative sign. So we'll have a negative x squared, negative 2x, and a positive 3. And all of this, again, will be over h. Now, a lot should simplify. Let's just make sure we do this very carefully. First, we have x squared minus x squared will add up to 0. Let's see, we have a negative 3. Plus 3 will also be 0. We have a positive 2x plus a negative 2x. That will be 0 as well. And I think that may be as much as we can simplify in the numerator. So let's see what's left. We have a 2xh plus h squared plus 2h all over h. Well, it looks like we can factor out h as a common factor in the numerator. So we have h times 2x plus h plus 2 all over h. And h divided by h is 1. So finally we'll be left with 2x plus h plus 2 as our final answer. You could have also simplified at this step, just making sure to be careful that each of the original 3 terms in the numerator is divided by h. So this will be our final answer for the difference quotient. Again, I know it might be a little frustrating to go through a very long mechanical process without understanding its uses, but it will be tied to average rate of change, which is a concept explored in later courses. Earlier I mentioned the vertical line test to determine if a relation can be classified as a function. Remember that we talked about the requirement for a function that no two ordered pairs have the same x coordinate and yet have different y coordinates. In other words, no two ordered pairs can be vertically stacked. So the vertical line test says that if it's possible for a vertical line to cross a graph of a relation more than once, then the graph does not represent a function. So let's look at example A, for instance. No matter what vertical line I try to imagine, it can never cross the graph at more than one point. And that's because there are no 2 points on this graph that are vertically aligned. That means that this passes the vertical line test and that graph does represent a function. In example B, however, I can easily find a vertical line that causes an issue. Here is 1 point, another, and even a third that all have the same x-coordinate of 0 and yet different y-coordinates. Because those points are vertically aligned, it fails the vertical line test, and therefore this relation is not a function. Similarly, for the third graph here in letter C, we have 2 points that can easily be found that are vertically aligned. These have the same x-coordinate, yet they have different y-coordinates, so this is not a function. And hopefully as we go through these examples, you're finding it easier and easier to apply the vertical line test. Here is a vertical line that passes through 2 points. Therefore, those points are vertically aligned. They have the same x-coordinate, different y-coordinates, not a function. In letter E, I think this is a function. No matter what vertical line we try to imagine, it will never cross through the graph at more than 1 point. And so it does pass the vertical line test. This is a function. Notice that in this little part of the graph, we have lots of ordered pairs that have the same y-coordinate, and that's okay. You can have different ordered pairs with the same y-coordinate. You just can't have the same x-coordinate. So we don't have any ordered pairs that are vertically aligned. This is a function. In letter F, again, we can try to imagine a vertical line at many different places, and yet there will be no vertical line that passes through 2 ordered pairs. I know it's kind of small to see here, but that is an open circle. That means that that point does not constitute part of the graph. So if you're thinking about this vertical line, we're still okay. This point is included, that point is not, and so we do not have points that are vertically aligned. That means that this is also a function. In fact, this is what's called a piecewise function, and we'll explore that later in this course. Next, let's look at how to determine the domain of a function given only its equation. When a function whose inputs and outputs are real numbers is given by a formula, the domain is understood to be the set of all inputs for which the expression is defined as a real number. Another way of thinking about this is that if we find any values of x that cause problems, then those x values have to be excluded from the domain, not included in the domain. For example, x values that would cause problems are those that would cause a denominator to be 0 because division by 0 is not defined, or perhaps we're looking at a square root and the variable is included underneath the radical symbol. Recall that if we're working with real numbers, square roots, those radicands, those quantities underneath the radical symbol, cannot be negative. They can be 0, they just can't be negative. So in order to find the domain, you have to look at values of x that are troublemakers and make sure that they are not included in the domain. Next, let's look at some of the basic types of functions. Polynomial functions are very common. In fact, they include linear functions. The function f of x is equal to a sub n times x to the nth power plus a sub n minus 1 times x to the n minus 1 power, etc. That would be an example of a polynomial function. Let me give you some examples. If we have f of x is equal to 3x cubed minus x squared plus 2x minus 7, that's a polynomial function. In this case, 3 is a sub n, and the 3 is the n. And if you look at the constant term at the very end, that's a sub 0, just trying to make a parallel for what all these labels could represent. The domain of all polynomial functions is the set of all real numbers. So the domain of any polynomial function is the set of all real numbers. That is the interval from negative infinity to positive infinity. In a rational function, we have f of x is equal to g of x divided by h of x. That means that we have a polynomial divided by another polynomial, and both include the variable x. This is one case where you have to be careful about the domain because division by 0 is not defined. So here's an example of a rational function. What about f of x is equal to x squared plus 1 divided by 7x minus 3? So the numerator is a polynomial, the denominator is a polynomial, and for the domain, we have to be careful that denominator 7x minus 3 can't be 0, which means that 7 times x can't be 3 if we add 3 to both sides, which means that x cannot be 3 divided by 7 if we divide both sides by 7. So in this case, we would say that the domain includes all real numbers except for 3 over 7. So to write this in interval notation, we'll say that the domain can include all x values from negative infinity up to but not including 3 over 7. Remember that open parentheses indicate that values are not included. And then we'll use the union symbol and pick up on the other side of 3 over 7. So these are equivalent. To say that x cannot equal 3 over 7 is to say that the domain includes all numbers except 3 over 7. I kind of refer to this as hitting the speed bump. If you can imagine the real number line, it's like you're cruising along, everything's good. Here's 3 over 7. We can't include it, so we have to jump over it and then pick up on the other side. A root function has the form f of x is equal to the nth root of some polynomial g of x. And because we're using radicals, we have to make sure that if the index of that radical of that root is even, that the quantity underneath the radical symbol must be either 0 or positive, cannot be negative. If, on the other hand, the index of the root is odd, then we won't have any restrictions on the radicand. So for example, that moved a little bit more than I wanted it to. For example, if we have f of x is equal to the square root of 5x plus 2, because this is an even index, it's an invisible 2 for the root, we have to make sure that 5x plus 2 is greater than or equal to 0. It can't be negative, which means that 5 times x must be greater than or equal to negative 2 if we subtract 2 from both sides, which means that x must be greater than or equal to negative 2/5. So in terms of the domain, we have to make sure that we are at negative 2/5 or greater. That means that that is our lower limit, which is included with no upper bound. On the other hand, if we had, let's say, f of x is equal to the cubic root of negative 9 times x to the 5th power. Because it is an odd root, there will be no restrictions on x. And again, the difference between these two examples is that this is an odd root, and in the previous example, there was an understood even root. So in this case, we would have the domain with no restrictions, all real numbers.